Okay, let's roll. Thursday you got a test. Today we're going to go over the last module. But first, let's get some different business out of the way. Usually I do not actually need a good reason to loathe the upper administration of this place, but they're really working hard to give me one. Does anyone else find it warm here?
Yes.
Okay. So I went around, we got 3 plugs at best. So let's just figure, I can't do this for Thursday, but let's figure out, would you prefer the white noise of fans? Is that going to be too disruptive either for note-taking or tests, or would you prefer this? I mean, either way is fine, it's up to you. How do you want to do it? Raise your hands for this. Raise your hand for fans. Okay, so I'll try and make them white fans. But I got 3 plugs, that's all I have to work with this entire room. I'll go try and find some relatively quiet fans, 1 in the back, probably 2 in the front, and we'll see how that goes because this is January. And you can imagine what this is going to be like as we roll along. So I apologize on behalf of the upper administration that I utterly loathe, but this is what we got, and we'll do the best we can. Okay, module 1.3. All right, other carbon fixation reactions, and more importantly, in some ways, why we need them. Now, this is just true, right? I know some of you probably look through this and think we're going to get a big environmentalism lecture. You're not. But the fact is that the Earth is warmer than it used to be in many places. And I thought this was a particularly illustrative example where we have a glacier turning into a not glacier within the course of a little over 60 years. So we are obviously in part of a global warming trend. That global warming trend is likely due to the injection of CO2 into the atmosphere due to industrialization. Now, that said, note that there were not a lot of industrialized things 150,000 years ago or 200 or 300,000 years ago. So there can be other reasons for carbon excursions in the atmosphere. But those carbon excursions are generally followed by extraordinary variations in temperature. So the fact is that we have global CO2 accumulating in the atmosphere. The fact is that the Earth is indeed getting warmer, and that is going to have probably some major consequences. So, here's the, we get to actually, with climate models, people will say to varying degrees of certainty how much temperature is going to rise in the next 100 years. But the fact is, even a relatively small rise in temperature is going to have some major impacts for global society. So depending upon whether we have a relatively small or a much larger rise in temperature, we're going to have major sea level rises, which are going to endanger coastal property. Right? It's not going to be overnight. You're not going to wake up one day and have the ocean in your backyard. But nonetheless, we're going to have to change how we do demographics in at least a number of portions of the world, including some of the specific atolls that will just completely go under. There are other predicted impacts in terms of unpredictable events like storms, how ecosystems what their carrying capacity will be, how we're going to maintain a food supply. So again, this is all just, I would argue, fact, not trying to say that we have man-made accumulation of carbon and, oh, look, it's all our fault. It's just there is an accumulation of carbon. It's probably man-made, and these are the likely consequences irrespective of the climate model you like or don't like. So there we go. Where we come in, I think, as scientists and engineers, is how to do a reduction in the amount of carbon in the atmosphere. Now, the viewpoint I will present, which is just my own, is probably slightly different than what you've heard in other classes or may have heard in general, which is I don't know what would happen if we ceased industrial activity today. And I think that it is very difficult, even with current climate models, to say anything other than it is likely that we would at least alter the trend of carbon accumulation and temperature, but we wouldn't necessarily reverse it. It's not clear whether we're already beyond the point of no return in terms of carbon accumulation and temperature rise. That said, irrespective of where we are, it's not like we're going to quit pumping carbon into the environment real soon, right? We don't have a lot of choices. Oil, coal, natural gas all have a predicted trend that goes up. They all have a carbon footprint, some more than others. Nuclear, which is really the only non-carbon option, and even there you can argue that nuclear has its own way of leading to environmental distribution of carbon, is not really going to, at least so far, see a grand uptick in use. Renewables will remain a small proportion of the overall energy balance. So even if we wanted to stop industrialization, go back to being hunter-gatherers and whatnot, it's not going to happen. So this is what we have to deal with. Increased carbon accumulation, which again, totally empirically, is going to lead to increased CO2, which is going to lead to increased temperature. Here's how various folks, at least one organization, the IPCC Special Report on Carbon Capture and Sequestration, has talked about how we might reduce the amount of emissions. Part of it is through conservation and energy efficiency, no doubt, just not being quite as profligate in our use of carbon. Going to nuclear, still just a tiny little piece of the picture. Coal to gas, use a less energetic or less something with less of a carbon footprint, but still a carbon footprint. Renewables, but look at this. Here's carbon capture sequestration, CCS. Now that can be by any variety of means, and in fact this report mostly talks about chemical engineering means for carbon sequestration, not biological means. But this is a biochemistry course, and so for you guys, the job, the mission, the task is how do we sequester carbon? How can we make a biological alternative to what is, nominally Armageddon? And, the Earth has dealt with this before. The rainforests grow up, they suck carbon in, they're a nice big carbon buffer. We're not going to make a rainforest overnight. What could we do? Could we establish new carbon sequestration pathways? It starts at the level of the molecule. And have these instantiated in organisms that we could grow in interesting places, in salt brine, in the ocean, on the tundra. Where could we do carbon sequestration? It all starts for you guys here. Now there are various levels of this. Just having a pathway doesn't ensure that it's going to operate in the right place at the right time. We saw that it was very difficult, in fact, to predict the balance between C3 and C4 plants, nature's own solution to carbon sequestration and to efficient carbon sequestration at higher temperatures, C4 plants, which indeed do better carbon sequestration at higher temperatures because of that lovely little carbon capture mechanism they use, capturing in one cell and pumping it interior for release. It's hard to predict what the ecology of that is. So this is not a be-all, end-all. What we're studying right now doesn't solve the problem, but it is a portion, in my view, of the solution. The more you know about what you could make, the more you might be able to contribute to organisms and eventually ecologies that will be able to deal with carbon rise. So this is where what I'm saying may have differed from, I used to have wonderful arguments with a really great woman named Camille Parmesan, who was in integrated biology. She was Nobel Prize winner in the sense of she was part of the UN report on climate change, so there was like several hundred Nobel Prize winners, but Camille was legitimately one of them. And so we used to argue a lot because Camille was of the sort of ecology mindset that said, look, we just need to reduce the amount of human activity. We need to go back to being able to not pump so much carbon in the environment. We need to see that the environment can recover from that. That's not a bad attitude. We do need to have conservation. We do need to change our carbon sources. That's all part of a mixture of solutions. But the solution I tend to like is an engineering solution. And it's not just a small-scale engineering solution, it's a global engineering solution. We will get to the point where we will have to consider across the planet how we're going to do carbon sequestration. You look over in China, where, I was in China in December, right? It really is true for those of you who are either from China, have been to China, or whatnot. There are times you cannot see your hand in front of your face. It's Victorian England over there, where there's so much carbon being pumped in the atmosphere that it's circa Los Angeles from when I was a child, right? There are these huge inversions that lead to the accumulation of ground smog. So we have to deal with this at a global scale. Biology is one of the few technologies that scales globally, right? Right? Okay, so what else do you guys know from even your own lifetime? Cell phones. Cell phones have clearly scaled. Electronics scale. We went from Alan Turing, who was clearly a space alien. No, there's no question. Alan Turing is a freaking space alien. So sorry, but Alan is amazing, of course, in many, 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 many ways, but setting out digital logic, setting out the basics for computation, to sticking some wires in germanium at IBM, to first giant room computers, to what you guys carry around on a daily basis. Clearly a scalable technology. And it's scaled because electronics is scalable and digital logic is scalable. And it's really weird because this sort of thing is very strange to me. I grew up in biology, right? From when I was your age, I grew up in the world of biology. So these things are weird to me. But biology is familiar to me because I've seen it cover the earth time and again. You know what happened during the course of evolution, you know that we went from a situation where we were anoxic to a situation where we had an oxygen-rich atmosphere because biology took over. So with engineering, and hopefully with appropriate planetary husbandry, we can be part of the solution. So this whole 2 lectures that were really sort of a warm-up, teaching you things you already knew, to today, teaching you things you don't know, is to give you some sense of how you might participate in solving this problem. So how do we sequester carbon? There's a surprisingly few number of mechanisms. And you've seen them now if you've looked through the notes. Here we have gluconeogenesis. It's the opposite of glycolysis. Glucose, glucose 6-phosphate, fructose 6-phosphate, fructose 1,6-bisphosphate, our buddy aldolase, dihydroxyacetone phosphate, glycerolide 3-phosphate, 3-phosphoglycerate yielding 1 ATP. Remember that? 3-phosphoglycerate, 2-phosphoglycerate, phosphoryl pyruvate yielding 1 ATP. Remember that? Pyruvate. And then that can go to lactate or ethanol for fermentation or into the Krebs cycle via acetyl-CoA. So we looked at all this. But of course, this can go the other direction. These reactions are all reversible, a la Maxwell's demons, some of them more than others. The flux-producing reactions here and here that drive this forward don't re-yield ATP. This is downhill energetically from the pyrophosphate in ATP to the monophosphate on glucose or the second monophosphate on fructose. So we hydrolyze phosphate when we're going that way. Going here through the aldolase reaction, this is what I've been saying all along. You can either run the electrons to cleave a carbon-carbon bond, or you can reverse the aldolase reaction to put together dihydroxyacetone and glycerolide 3-phosphate to make fructose 1,6-bisphosphate. This is all reversible, including the 3-phosphoglycerate to glyceraldehyde 3-phosphate reaction, where we have a reducing equivalent participating. This is the hard one, though. Phosphoryl pyruvate to pyruvate. That doesn't easily reverse. Now here we made lower energy phosphates. Here we have a reducing equivalent participating in the reaction in a way that made it nominally reversible. But once we make ATP here, this goes way downhill. Phosphoryl pyruvate to pyruvate. Basically, this is a very high energy phosphate compound. This is a less high energy phosphate compound, and going backwards becomes very difficult. So there's a shunt around this, a so-called anaplerotic reaction. Now, anaplerotic is biochemist E's for refill. This is a set of reactions that allow you to refill the Krebs cycle. Because you may wonder, it's a cycle, right? If I have one cycle, then I put in acetyl-CoA and I get 2 CO2s out. If I have 2 equivalents of cycle, I can make twice as much CO2. If I have 10 equivalents of cycle, I can make 10 times as much CO2. But where does the cycle come from? Where do the intermediates in the cycle come from? What is the capacity of the cycle? How do, it's a wheel, but how do I make the wheel bigger? Well, the way to make the wheel bigger is you make the intermediates. And the way to make the intermediates is to make them from other things. And in this case, pyruvate not only feeds the Krebs cycle with acetyl-CoA, but can be carboxylated to make oxaloacetate. So this is an anaplerotic, a replenishment reaction for the Krebs cycle. And we'll look at the mechanism of pyruvate carboxylase in a minute. Phosphoryl pyruvate can also be carboxylated to oxaloacetate, the PEP carboxykinase reaction. When we run it in the gluconeogenic direction, we're actually losing CO2. So we gain a CO2, then lose a CO2. What that does is that converts pyruvate to oxaloacetate, the anaplerotic reaction, but we can also take pyruvate and send it back up through to glucose. So this is also part of gluconeogenesis. It just happens to go through oxaloacetate because we can't readily reverse the pyruvate kinase reaction. Okay, so there's your first CO2 fixation. There's actually 2 reactions there. Here is a chart of all of the various CO2 fixing reactions, save for a couple. So this is your palette. When you think about it, when we look at these weird pathways in just a little while, you'll see that they use some of these reactions because there aren't many choices. The one we just talked about was pyruvate carboxylase, pyruvate to oxaloacetate via ATP. We burn an energy coin and bicarbonate. We also talked about the phosphoryl pyruvate to oxaloacetate reaction, where we just have a bicarbonate participate. That's the PEP carboxylase reaction. If we also have an ATP participate, it's the PEP carboxykinase reaction. I actually forget which one of those 2 they showed on the last slide. Yeah, so they actually have a GGP equivalent in there, so that's more like the carboxykinase reaction there than the pure carboxylase. And finally, we can also go from pyruvate to malate with the addition of a bicarbonate via a reducing point NADPH. So here's 4 enzymes, and we're going to look at the mechanisms, the basic mechanism for carbon capture. We'll start with pyruvate carboxylase. So it is a biotin-mediated reaction. Now, I've talked about our various coins, right? ATP is our energy coin. Nicotinamide, our redox coin. Biotin is our 1-carbon carrier. Now, it's not the only 1-carbon carrier. It's really a good carboxylate carrier. What's the name, just in case you were paying attention in the other sets of classes, what's the name of the other 1-carbon carrier we sometimes use? Claudia, Lay. Claudia. Hey, Claudia. What is the name of another cofactor? That's a 1-carbon carrier. You don't remember? That's an excellent answer. Okay. Hints all around. It is very important in pregnancy. It's also known as vitamin B. What's that? Folic acid. Yeah. So folic acid is our general 1-carbon carrier. Folic acid will carry carbon, and we'll see this in Module 3. Module 3 is where we'll get heavy on folic acid, which will, in various ways, carry methyls, methylines, methylamines, aldehydes, and even carboxylates if we force it to. But biotin is a really good 1-carbon carrier for carboxylates. So what we do is we charge up biotin here such that we can readily have biotin move someplace else. Now, here what's obviously happening is we've charged up biotin with carboxylate, and we'll see how that works. And then in the guts of an enzyme, we release CO2 so that it can be added to pyruvate. What form of pyruvate are we going to add CO2 to? Carlos Hernandez. Carlos. See how I say? Oh, sorry, Carlos. I'm so sorry I missed you. Yes. What's that?
I was just thinking.
That's
what was the question?
Okay, so the question is, here's our buddy pyruvate.
Yeah.
What form? So here's a test. Oh my gosh, I have to draw a mechanism. What form do you draw pyruvate in that will most readily allow it to make a new carbon-carbon bond to CO2? So here it is, looking sort of like pyruvate. But, yes, very, 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 very good. So enol is your form for carbon-carbon bond formation. And this is going to be true many times today, so that's why, thank you very much, Carlos, we wanted to get it out of the way. The enol form will allow attack on CO2 and the formation of a new carbon-carbon bond. There is the enol form. Now here's this question, why have addition of CO2 to biotin just to release it, right? Why didn't we just cut out all the middlemen here, have bicarbonate turn into CO2? That's an easy equilibrium. That's what your blood does all the time anyway. So your blood buffer is bicarbonate. So why did we need all this? Why did we go through this sort of biotin sequestered intermediate? Chad Wang. Chad, what do you think? Why did we do that? Why not just start, right here, cut out all this nonsense?
At first I thought it would be because biotin is actively delivering CO2 to the substrate.
What's wrong with that answer? I like that answer a lot. What was your second answer?
I was also considering how the nucleophilic reaction could be where biotin is carboxylated and it just directly...
Excellent. So that was a more mechanistic explanation. Instead of it being released as CO2, you actually have attack on the carboxylated biotin. You actually have sort of a concerted reaction. That's a very good answer too. Both of those are excellent answers, Chad. In this particular instance, what I wanted to point out was, just as in C4 plants, remember, we had sequestration of carbon in one cell and delivery at a higher concentration to another cell for uptake and for addition. Chad's first answer was, well, if we sequester it onto biotin, which is actually on a little swinging arm itself, which we'll see in just a minute, then it can deliver it right to an enzyme active site, so that enzyme active site has an increased concentration of CO2 at the point at which there is an enol ready to receive it or to attack it. So you can think of this as an entropy trapping mechanism. Rather than CO2 flitting in and out, as it does in Rubisco, here we deliver CO2 directly to a substrate for carboxylation. Okay, Now, the first part of the question before was what was the intermediate for loading up biotin? They just had a couple of arrows there. Here we see that the bicarbonate form of CO2 can be phosphorylated to make carbonyl phosphate. So that's carbonyl phosphate. Carbonyl phosphate, in turn, can be attacked by biotin. This is just showing the deprotonation of biotin, but the actual attack of biotin on carbonyl phosphate kicks out the phosphate. So we used our energy coin to create a version of CO2, bicarbonate to carbonyl phosphate, where the phosphate would serve as a leaving group. In other words, exactly the same as multiple other reactions we've seen where we use our energy coin to pass along a high energy phosphate to act as a leaving group. So once it can act as a leaving group, it's easy to carboxylate biotin. Okay, so summary of reaction types. Phosphorylation, which we just saw again. Isomerization via enol, we saw the importance of that for carbon bond formation, which we talked about again here. Isomerization or epimerization also go via enol. Retroaldehyde cleavage, and it's reversed, the aldol reaction, redox reaction. Oxidative decarboxylation, that special series of steps that proceeds through thiamine pyrophosphate and lipoic acid and ultimately ends up with electrons, hydrides, on FADH and then NADH. Again, carbon addition via enol, dehydration and rehydration, like isomerization. 2-carbon transfer with thiamine pyrophosphate, a bit like oxidative decarboxylation, but instead of this being eventually passed off to, say, acetyl group, or to a CoA, here we're going to pass it on to another sugar. This was part of the Calvin cycle, part of the shunt that basically took 5 times 3 and made it 3 times 5, and finally we just learned biotin-mediated carboxylation. The point here for saying all of these words is to remind you, I'll get you, you're Elizabeth, right? Yes, I'll get you in 1 second, thank you. Is to say you've only learned a small number of reaction types. So when confronted with new chemistry or having to fill in new chemistry, I'm not going to, invent nuclear reactions. There you go. There's your palette. Yes, Elizabeth. Sorry.
On the last slide, we're adding on a phosphate, but I don't see us adding on the biotin. Can you show that? On the.
Okay, here we go. So there's my phosphorylated carbonyl phosphate. Right. Here is the nucleophile nitrogen. Now again, I've made an enamine here. So here we're going to re-establish the carbonyl. Attack goes the bond on CO2. Pop goes the phosphate. Okay, very good. All right. So, limited number of reaction types. Other questions? Incidentally, you are welcome to stop and ask me questions. It's terrifying, right? Because you're like, oh, everybody will think I'm stupid. No, everybody else is confused too. They'll think you're a freaking hero, okay? So, be a hero. Ask questions, right? And incidentally, for those few of you who came to my office hours, you realize that I actually will answer questions. I know this is a big step forward for you all to think that I might be an actual resource of education, but you paid me money to be here, so use your money wisely. Ask me questions. All right. All right, very good. So PEP, carboxykinase. Can I just skip over one? Yes, thank you, because I was going to say, where's my PEP carboxylase? You were doing that first. Here's PEP carboxylase. It's really cool. It's actually sort of just like what we saw with no biotin. Look what bicarbonate cleverly does. It adds itself to phosphoryl pyruvate. What is that thing? That's very strange. So it makes this nominal, sort of pentavalent intermediate, but that's the transition state. But really what this is the high energy donor. So rather than ATP phosphorylating bicarbonate, PEP phosphorylates bicarbonate to make carbonyl phosphate. So it's like it's using the same substrate that's going to be carboxylated also as its energy source. I think this is cool. So there we go, carbonyl phosphate then, well, how boring, enol, attack, pop goes the phosphate, on goes the carboxylate. Just the same as the biotin reaction, but with no biotin, and with activation not via ATP, but directly via PEP. Okay, PEP carboxykinase. Now, I've run this in the PEP synthesis direction rather than the carboxylating direction. This is the decarboxylating direction. In the carboxylating direction, look what's going on here. We have a enol to begin with. We have an enol once we phosphorylate it, I'm running backwards, I need to dephosphorylate it. So here's the phosphorylated enol. Here we're going to donate to ADP to make ATP. So that makes just the enol version of pyruvate. And then that enol version of pyruvate can then attack CO2, which again we've seen many times before. But the difference here is we're not attacking a phosphorylated version of carbon dioxide. We're not attacking carbonyl phosphate. We're just attacking good old CO2. Now, that said, that's more like the biotin-mediated reaction we saw just a few moments ago. Oops. Sorry. Yes, because here, oh, I'm sorry, so that's to load up biotin, but to actually potentially grab CO2, it was on biotin. So biotin was your leaving group here in one of the mechanisms that Chad alluded to, or CO2 is released when we just attack it with an enol. With the carboxykinase reaction, we actually have, again, a direct attack on CO2, no leaving group. And here we have a direct attack on CO2, going in the reverse direction, no leaving group. Which raises the interesting question of, well, why the heck do we go through PEP in the first place? Why all that mucking about with phosphate? The answer being that this actually could potentially help drive the reaction forward. We have a coupled equilibrium. Now, you probably learned about coupled equilibrium in the past, where you burn an ATP in order to get someplace. Here, we're making an ATP in order to get someplace, but remember, phosphoryl pyruvate is an incredibly high energy compound. So this is a coupled reaction where energetically, even if this step is uphill, overall, it may be downhill. Okay. Now, finally, we have the carboxylation of malate with a subsequent reduction. Here we once again, where's my CO2? My CO2 is someplace. Ah, there it is, CO2. So forget the tautomer. I mean, the tautomerization is again just to get us to an enol form. But look, this is just essentially pyruvate. This is the enol form of pyruvate. Once again, that enol will attack CO2 to make oxaloacetate, and now we will reduce that to malate. So the reason I bring that up is just as we have a coupled equilibrium here with the formation of ATP, we have a coupled equilibrium here with the reduction of oxaloacetate to malate, where NADPH as our redox point can drive that reaction forward. So the PEP carboxykinase reaction is similar to the malate carboxylation reaction, or rather the pyruvate carboxylation reaction that forms malate, in that both have coupled equilibrium. Okay, now let's go back to this slide. This is sort of our lingua franca for four, at least, of the carboxylation reactions that we now know. In pyruvate carboxylase, we saw that CO2 was attacked from an enol form, and we had a couple energetics to reduction. In pyruvate, where do I want to be next? In PEP carboxykinase, here we go, we saw we had an enol form of pyruvate attack CO2 with the concomitant production of ATP. So there, again, that was a coupled equilibrium driver, that was a coupled equilibrium driver. For the PEP carboxylase reaction, which I think is sort of one of the really cool ones, we actually make carbonyl phosphate and then can attack the carbonyl phosphate to make oxaloacetate. In the pyruvate carboxylase reaction, that's the biotin-mediated reaction, where biotin becomes our leaving group via carbonyl phosphate to load up that biotin. Okay, now one last carboxylation reaction. This isn't in your notes, but you can find it in your book. I just remembered that I needed to put this one in too. This is once again going to be mediated by biotin. So the biotin carboxylase you already saw will take bicarbonate, phosphorylate it, and then make the carboxylated form of biotin. Then, however, acetyl-CoA, so not the enol form of pyruvate, but the enol form of acetyl-CoA will attack to make malonyl-CoA. Right? So the CoA is still on there. This went via the enol form. We had the enol attack to pick off the carboxylate from biotin. So it's very similar to the pyruvate carboxylase reaction, but this trans-carboxylase is using acetyl-CoA as one of its substrates. This is the starting point for fatty acid biosynthesis. We'll see this again at the beginning of Module 2. Module 2 is sneakily about fatty acid biosynthesis, which you didn't learn in F, but we'll learn here. But we're just going to learn it in passing on the way to a cornucopia of interesting compounds. But I should have brought this forward. I knew I had it in there, but I forgot that I needed it here. So this is our 5th carbon fixation reaction. And so again, you've seen biotin-mediated carboxylation. And again, all of those reactions essentially are carboxylation or decarboxylation reactions, in which if it's decarboxylation, we fold electrons into CO2 and break a carbon-carbon bond. Or if it's carboxylation, all the ones you've seen so far go from an enol form to form a new carbon-carbon bond, where CO2 becomes a carboxylate. We have a developing negative charge on the carboxylate. All right, so now we are to the paper that I assigned. And really the function of that paper was to give us lots of pathways to look at. Now nominally, these are the 6-ish pathways for carbon fixation. If we're going to save the planet, this is our palette from nature. Now, what's interesting about our palette from nature, in my point of view, is how much overlap there is between the different reactions and what latitude that gives us to engineer new carbon fixation pathways. So, A, I probably know carbon fixation pathways beyond those 6 that I might test you on, or B, I could invent a new carbon fixation pathway and test you on, or I could even ask you to invent a new carbon fixation cycle. Although the latter, perhaps for the first test, is a little sort of overachieving. We'll wait for the final. So, in any event, you know this one. This is the Calvin cycle. This is 5 times 3 equals 3 times 5 via Rubisco. Where's my buddy Rubisco? Oh, where is my carbon fixations? Yeah, there we go. Ribulose 1,5-bisphosphate. In the ribulose 1,5-bisphosphate, carboxylase oxygenase, Rubisco, makes 2 3-phosphoglycerate molecules, which then do a little glycolysis for us to get to glyceraldehyde 3-phosphate. Then there's all of those interminable transketolase, transaldehyde steps to get you ribulose 5-phosphate. Also, there's a couple of epimerizations or isomerizations in there, which, again, from your list of reactions, go via double bond intermediates. We burn an ATP to get up to ribulose 1,5-bisphosphate, and we do it all again. The only problem, of course, with this cycle being, as we talked about last time, the fact that it's very difficult for Rubisco to distinguish CO2 from oxygen, and therefore we have a cycle where we make only 1 3-phosphoglycerate, and then we make glycolate, and we have to recover the glycolate somehow. So, we went over that last time, so I'm not going to go over it this time. I'm just saying one of our 6 is here. The second of our 6 is the incredible Lindahl pathway. So this is, again, if at different time, in different place, if I did carbon fixation later in the term, we'd learn this. Look at all the folate chemistry. Oh my gosh, you talk about being a 1-carbon carrier. CO2 onto formate makes the acid version of formate reduced to the formyl, reduced to the methanol, reduced to the methylene, reduced to the methyl. So completely reduced. And then somehow, miraculously, when we take CO2, reduce it to carbon monoxide, this methyl tetrahydrofolate and carbon monoxide can get together. This is a very, very, very special reaction. It occurs only in certain species of bacteria that require special cofactors for it. So this is a brilliant pathway to make acetyl-CoA. And it's pretty simple. 1 plus 1 equals 2. And we never go above 1 here. We're just sort of transforming 1. We never go above 1 here. We transform it. And somehow the magical enzyme with the magical cofactors at the end makes acetyl-CoA. Great pathway, anaerobic, find it in all sorts of archaea, but we're not going to worry about it. Energy source is hydrogen. You can now see why it's anaerobic. All right, now, this one is easy too. It's the reverse of the Krebs cycle. It's literally called the reductive Krebs cycle, where we have now citrate, which will split off acetyl-CoA to make oxalyl acetate rather than adding acetyl-CoA to oxalyl acetate. Now, we talked about the arrow pushing for that reaction, where that also will go via sort of the enol version of acetyl. And so you can imagine how the reverse condensation works there. And then we reduce oxalyl acetate to malate rather than oxidizing malate to oxalyl acetate. Malate can be dehydrated to fumarate. One of the other great things about when you see things like this, they don't always have all the substrates written in, all the products written in. That's sometimes for you to find out. And this particularly simplistic form is both great because we can compare things across pathways, and a pain in the butt because we're trying to figure out what here via the bizarre sort of colored nomenclature here. But here's our double bond formed during dehydration. That double bond is reduced with FADH as electron donor to succinate. Succinate is charged up to be succinyl-CoA. Succinyl-CoA. Now we're going to add, there's our 2 carbons in, there's going to be our 2 carbons out. 1 plus 1 is 2, but only via the cycle. And we definitely go above the level of 1 carbon here, unlike the Lindahl pathway we saw before. So here we have a reverse of oxidative decarboxylation. Here we have a reverse of a different oxidative decarboxylation. Isocitrate to citrate is an isomerization that proceeds via double bond, which you've seen before. So it's just, there's the Krebs cycle. There's the reductive Krebs cycle. The reductive Krebs cycle can grab 2 CO2s. The reductive Krebs cycle is actually, it actually is present. It's in bacteria that have a lot of energy from light or sulfur. So photosynthetic bacteria sometimes use this. And you might imagine why. A photosynthetic bacteria, photosynthetic anything, has essentially infinite energy and infinite reducing equivalents, right? If you're a plant, you're not particularly worried about energy. You're making biomass. You're just sitting there, sucking up sun and making biomass. So plants are amazing, and so for them, the problem is capturing enough CO2, but they have ATP as much as they could possibly want to a first approximation, and they have about as much as NADPH as they want. So you can run the reductive Krebs cycle in a photosynthetic organism because you have a lot of ATP and NADPH. It's an anaerobic cycle, which is interesting. It's exactly the opposite of what you might imagine for an oxygen-producing bacteria. But sometimes we have photosynthetic organisms that have different electron sinks like sulfur. All right, now, here's where we're getting in. Now, up till now, right, everything's game for test questions, right? What kind of questions would I ask you about the Calvin cycle? All right, well, the Calvin cycle where it goes 3 plus bleed to 6, 6 plus 4 to 9, what is it, 9 plus, 6 plus 4 to 3 plus 7, or whatever. I should go back. I should go back. I should be able to do that in my head, sorry. There. 6 plus 3, right? So here we go. What kind of questions will I ask you about the Calvin cycle? Well, clearly, the mechanism of the aldolase is open for questions. But the nice thing about that is, it's all the same mechanism. We have the addition of 3 carbon to 3 carbon, or the addition of 3 carbon to 6 carbon, or the addition of 3 carbon to 7 carbon, or another. So addition of 3 carbon right, addition of 3 carbon to 4 carbon. Sorry, addition of 3 carbon to, let me go on train. Aldolase here, ketolase there. Sorry, so we've had the addition of 3 carbons to 3 carbons, or the addition of 3 carbons to 4 carbons. So you should be able to do that aldol synthesis reaction. It's just the reverse of the aldolase reaction, which you know. The transketolase reaction that runs through thymine pyrophosphates, perhaps a little more tricky, where we move 2 carbons from on top of that 6 to that 3 to make 5, leaving behind 4. Or we move 2 carbons from on top of that 7 to 3 to make 5 and 5. So I can obviously ask you about the mechanism of transaldolase or transketolase, and you would be able to respond easily because you got it in your notes and you will have practiced what that would do. The other type of question I might ask you, let's say, would be, why is it that, okay, so this is a why question, I wouldn't ask you this, but why is it that I can get away with doing this entire pathway with 2 enzymes, transaldolase and transketolase? Brianna, why is it that even though I'm doing 4 reactions with a bunch of different substrates, I can get away with only using 2 enzymes here? What is it about those enzymes that lets me get away with this?
I'm not sure.
Okay, so transaldolase does this and this. Is transaldolase specific for its substrate?
No.
No. Transketolase does this and this. Is transketolase specific for its substrate? Okay, if I gave you a 20 carbon sugar and a 62 carbon sugar and asked you to do a transketolase reaction, could you do it? Yes, you could, because it's the same reaction. So it would not be unreasonable to expect that you will see sugars you have never seen before, but you know, as Brianna has told you, that the generality of the fact that these are semi-specific enzymes with a common mechanism would let you easily tell me if I had a 20 carbon and a 62 carbon sugar and I was doing a transketolase reaction, you would be able to draw the 22 carbon sugar and draw the 60 carbon sugar that was left over. That's reductio ad absurdum. I'm not going to have you draw 60 carbon sugars. But you get the point, right? You can do anything with this. You can make 20 carbon sugars. You can do anything. And it just happens that the carbon flux is such that 5 times 3 easily leads to 3 times 5 here in the Calvin cycle. But in fact, the substrate non-specificity of these enzymes does lead to other products. You can make 9 carbon sugars, you can make 10 carbon sugars. These are great enzymes because they are semi-specific and they just do the transaminase to transketolase reaction. All right, now don't go getting crazed on me. Sorry. Right. Okay. Wait, come back to it. Yes. Right, no, soon. Okay, great. All right, so for the pathways, you know, okay, Lindoll's off the table, crazy anaerobic one carbon fixation off the table, but I can ask you questions about the Calvin cycle, likely mechanism questions. I can ask you questions about reductive Krebs cycle. Those would be easy because you know the forward reactions, and you push electrons for the reverse reactions. But now we get a little more interesting. I'm just pointing out that of the 6 pathways that I expect you to really know for carbon fixation, 2 of them you really do know pretty well by now, even from just having had biochemistry BCH339F, and now we're going to learn some new ones. But what I want you to draw from this is not, oh my gosh, I will now memorize in its entirety the dicarboxylate 4-hydroxybutyrate cycle, but rather, what are the pieces of the cycle? How did you construct the cycle from basic knowledge? If you were an engineer, either at the origin of life or now, how would you construct cycles? All right, so first reaction here. Acetyl-CoA to pyruvate with the addition of CO2. Have we seen that reaction before? The answer is no, we haven't actually, right? We saw a variety of ways pyruvate could add CO2 to make oxaloacetate, or phospholynyl pyruvate could make pyruvate or malate. We saw how acetyl-CoA could make malonyl-CoA, but we have yet to see how acetyl-CoA could make pyruvate. So that's actually sort of a new reaction here, maybe not a good way to start in a modular pathway. I just wanted to point out this will probably nonetheless go via the enol form of acetyl-CoA to make pyruvate, but it may be a different addition than the one you're used to for malonyl-CoA. We saw malonyl-CoA adding CO2. Essentially, if you add to the other end, you get pyruvate. Okay, pyruvate to phospholynyl pyruvate via a phosphorylation reaction. There is just the step that I told you nature abhorred. We abhor going uphill here, but apparently in these bacteria we have more than enough energy to push that uphill. We can really drive it with ATP concentration, but that's very far up here. Now we're to a reaction we know. PEP carboxylase here to make oxaloacetate. Now, oxaloacetate to succinyl-CoA. Where did that reaction come from? Jeff, Zia. Jeff. So, we're just going around. New reaction. Phosphorylation, albeit uphill. PEP carboxylase, a reaction we just learned. Where's this reaction from, Jeff? Oxaloacetate to succinyl-CoA.
Krebs cycle?
Yeah, that's a Krebs cycle reaction, but it's a little funny because you know what we're used to is essentially oxidative decarboxylation to get to succinyl-CoA. This is not that. 4 carbons, 4 carbons. So, in fact, this is a little more complex than the Krebs cycle, but these are both Krebs cycle intermediates. That reaction is actually a little like this one. You'd have to figure it out. So these are good. This one and this one are good advanced questions for you. But now, succinyl-CoA to succinate semialdehyde. What the heck is that? You, Mom. You. Hello. So, what happens from here to here, you? First of all, what's a semialdehyde? That's a funny biochemistry term. Biochemists have all sorts of funny terms. Okay, so a semialdehyde is an aldehyde. All right. The reason it's a semialdehyde is that one end's a carboxylate and the other end's an aldehyde. So at one end you have the carboxylate of succinate, but at the other end, instead of having the other carboxylate of succinate, which normally you would have in the Krebs cycle, we have an aldehyde. So succinate semialdehyde is succinate with an aldehyde at one end. So we went from the succinate equivalent, succinyl-CoA to succinate semialdehyde. What happened here? What happened here?
Oxidation.
Okay, very good. So in fact, it was a reduction. This is at the state of a thioester. This is at the state of an aldehyde. And again, I know that I'm doing it from this pathway. We could equally well do it from this one, where the substrates are better drawn out, but I wanted to start here. So, and the other thing is, note that we've lost the CoA. Now, in a lot of these pathways, the CoA comes and goes. But here we have an acid equivalent being reduced to an aldehyde. What is the nucleophile for the acid equivalent being reduced to an aldehyde? What is it that's going to come in and attack? Mahmoud Kabani. Mahmoud, what are we going to have come in there and attack?
Sorry, can you repeat the question?
Right. Cool. Here we have an acid equivalent. It's actually a thioester. Here we have an aldehyde. I'm going from the acid oxidation state to the aldehyde oxidation state. Something is coming in and punching that acid into being an aldehyde. What is the nucleophile that's going to change the redox state of that acid to an aldehyde? When we use a redox coin, that's just meant to be a redox coin. It's actually a protein, but it ultimately is connected to one of our redox sources, NADH or FADH2. What is it that we're doing?
The hydrogen, the proton?
Almost. There you go! Yeah! All right, so as a nucleophile, we're donating H double dot, right? The hydride, because we're reducing this. Okay, good. So there we go. That's just a reduction. So what was the leaving group? Hydride in, CoA out. Hydride essentially nucleophilically attacks and punches out CoA. Right? So if I asked you to draw that reaction, you would be like, oh, so simple. All right, what's going on in this next step? Succinate semialdehyde to 4-hydroxybutyrate. Ria Patel. Ria, hello. Ria, what's happening here? What's happening here? No, sorry. Okay. So succinate semialdehyde. I got a carboxylate, I got an aldehyde. Now you have to ask yourself, what in the world is 4-hydroxybutyrate? Butyrate. 4-carbon acid. Here's my acid. At the end here, I now have an alcohol. Acid aldehyde to acid alcohol. What happened? Something happened.
A reduction.
There you go. And what was my nucleophile for reduction? There you go. Use it. There you go. Excellent. And again, here it's a little more obvious. There's our buddy NADPH able to do the reduction. So this now gets us a little out of Krebs cycle intermediates into 4-hydroxybutyrate. Now we're going to somehow gain back CoA. How did we gain back CoA, and why does it involve an ATP? That's what this slide's about. This is not in your deck. I put this in because I realized I needed to tell you this because you haven't had fatty acid biosynthesis. Well, when you take an acid of any sort, you can make the mixed anhydride. In this case, we're making the mixed anhydride to AMP itself. But this is like 1,3-bisphosphoglycerate. In that, we have an acid, phosphoric, and an acid carboxylate to make a very high energy bond. CoA can come along, pop out AMP, and form the thioester. Acid, mixed anhydride, thioester. So that's all that's happening. Whenever you see CoA addition, you probably should see that there's an ATP involved. Now what they don't have is CoA come in. Just as previously when we went from succinyl-CoA to succinate semialdehyde, we had a reducing equivalent come in, but we don't actually show the CoA going out. Why do I give you these awful figures that don't have substrates for products or leave things out? Because this is real life. This is a paper from the literature. This is what you're going to have to deal with throughout your careers. You will not be spoon-fed every little thing. You have to derive it for yourself. You have to be able to see, oh, right, CoA went away. Why? Where? Oh, right, CoA came back. Why? Where? How? All right, 4-hydroxybutyryl-CoA to cryptonyl-CoA. How did we make cryptonyl-CoA? Dan Carlisle. Dan, where's Dan? Oh, there you are. Hello, Dan. How did we make cryptonyl-CoA from 4-hydroxybutyryl-CoA? And even in our stick figure models here, you can see something that has happened.
Decarboxylation.
Ooh, still got to work. See, carbon, 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 carbon. 1, 2, 3, 4. Carbon, 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 carbon. 1, 2, 3, 4. But we do have a new thing there,
You double bond.
new double bond. How do you think we made that double bond? Note that, again, this is not a complete diagram. Note we have no reducing equivalents. What did we do to make our double bond? We took a hydroxy at the end there. And
Dehydration.
bingo! All right, excellent, good job. Dehydration to make protenyl-CoA. And then we do what to make 3-hydroxybutyrate? Amira, not Amir, Hydar. Amira, hello. Amira, what do we do to go and make 3-hydroxybutyrate-CoA?
You got rid of the carboxylate.
No, we still got 1, 2, 3, 4. We still got 4 of them. Right, 4. We just, what? Sorry.
Did you hydrate it?
Yes, we did a dehydration and then a rehydration. Where have you seen that before? Where have you seen a dehydration followed by a rehydration to move a hydroxylate? There you go, aconitate. You knew it too anyway. So where we went from citrate to isocitrate. That's citrate to isocitrate. That's isomerization, 2-step, with an intermediate. You guys know all this stuff. Almost home. Hydroxybutyryl-CoA to acetoacetyl-CoA, a simple oxidation of the 3-hydroxy to a carbonyl. You don't know this reaction. Oh yes, actually you do, because you did fatty acid degradation. This is the terminus of fatty acid degradation, where you have a thioester formation. Here, actually, we have CoA coming in, attacking a carbonyl, and splitting a 4-carbon molecule into a 2-carbon molecule. What does the cycle do as a total? 1 plus 1 equals 2. 2 carbons in, 1 carbon out, and in between, 2 reactions you didn't know. This one, which is essentially attack on a carboxyl, on a CO2 from an enolate, and this one, which is a little more tricky. Several things happen there. But otherwise, oh yeah, we sort of know this stuff. We learned this carboxylation. These are just reductions. We put a CoA back on, dehydration, rehydration, oxidation, and then splitting of a 4-carbon to 2 2-carbons via the same process that's present at the end of fatty acid degradation. You know this cycle. This is yours. You own it now because you own the component reactions. Okay. Oh, yeah, we did that. Let's do a different one. Now, 3-hydroxypropionate, 4-hydroxybutyrate cycle. And let's look at this version of it because it actually has structures. So one thing you can do to test yourself is to go from the paper that doesn't have enough information and draw the structures. If you can draw the structures, you're halfway there. And then you have to ask yourself the same questions I'm asking you right now. How does it work? All right. So, acetyl-CoA to malonyl-CoA. Do we know this? Oh, yes, we do, because we learned it. This is how we start fatty acid biosynthesis as well, to make malonyl-CoA. Malonyl-CoA to malonate semi-aldehyde. Oh, I am such a boring person, I will ask yet again. Perla Delgado. Perla, what is going on there? So here is malonyl-CoA. Here is malonate semi-aldehyde. What was my nucleophile? What was my leaving group? What's that? Oh, you're one of the soft. What's that? Acetyl-CoA is in there. There's no doubt. There it is. But I've already made malonyl-CoA. I'm going to malonate semi-aldehyde. Something attacked and something left. What attacked? What left? What are our clues? There's our buddy a redox point, NADPH. And there's something left over at the other side of that arrow. Hydride attack, CoA leads, acid equivalent bioester to aldehyde. 3-hydroxypropionate. Now we're going to, in typical weird fashion, remake it into a CoA compound. Pop goes the CoA, pop goes back on, oh sorry, missed from 3-hydroxy, from malonate semi-aldehyde to 3-hydroxypropionate. Go down the oxidation chain one more time. Aldehyde to alcohol. We even saw this in the last cycle. We saw it at the 4 level. Succinate semi-aldehyde to 4-hydroxybutyrate. Malonate semi-aldehyde to 3-hydroxypropionate. Same thing, except 3 carbons rather than 4. Now we'll put CoA back on. We'll do that via phosphorylating in some way the carboxylate, and then having CoA come in and kick out AMP. And we saw that. 3-hydroxypropanyl-CoA. Acrylamyl-CoA. What kind of reaction is that? Oh, I am so boring, I am so boring. Robert Agulto. Robert, what kind of reaction is that? Even the water leading tells you dehydration. Then we reduce the double bond using our reducing coin, NADPH, to propenyl-CoA. Look at all this hard work to get from acetyl-CoA to something that's one methylene longer. That's all. We went from I'm a methyl adjacent to a carbonyl to I'm an ethyl adjacent to a carbonyl. All that work to get to propenyl-CoA, but the work sort of makes sense. We had to add the CO2, and then literally we had to sort of reduce it down to the methyl group, and we reduced it down to the methyl group via aldehyde, alcohol, dehydration, reduction. Right? And you've seen this before actually in fatty acid biosynthesis and fatty acid, sorry, you haven't seen that, but you've seen it in fatty acid degradation all the way to the reverse. All right, now we're going to add our second carbon. Added one here, going to add one here. What is the form of propenyl-CoA that is there for carbon addition? Vismaya Kandapali. Vismaya. Vismaya Kandapali. Okay, sorry. Chaitanya Kasim. Chaitanya, what form do I draw propenyl-CoA in order to attack that bicarbonate? What's it called? What form of propenyl-CoA? How would I draw propenyl-CoA so as to attack CO2? Just as we were doing with, shall we say, malonyl-CoA up here when we added CO2, or with any of the other carboxylations. What's the form of the compound? Enol. Great. Just driving it home here. And also driving home, it's all the bloody same. It is really boring. Sorry. So here we have propenyl-CoA in its enol form. What's it attacking? Well, it's attacking, you just said, CO2. Oh, wait. There's an ATP in there someplace. What's it attacking? Carbonyl phosphate, and we're going to kick out a phosphate eventually. So we actually make an activated form of this. So this is very akin to how we did the PEP carboxykinase reaction in making a carbonyl phosphate intermediate. Now, look where we added that CO2. This gives proof to what was just said. The enol form of this adds to that carbon, making a branched carbon species, making S-methyl-malonyl-CoA. Now, S-methyl-malonyl-CoA is going to become succinyl-CoA. This is a very odd reaction, which I will jump to right now. You saw this if you were in Barrick's class. Again, I'm borrowing some of Barrick's slides just to prove to you if you've seen this before. When you do odd, when you do odd chain fatty acid degradation, you have a 15 carbon fatty acid, you chomp it off 2 by 2 by 2 by 2 until you have 3 left, propenyl-CoA. What happens then is you carboxylate propenyl-CoA via propenyl-CoA carboxylase. Now we just saw propenyl-CoA carboxylase also going to methyl-malonyl-CoA, right? So it's this reaction that you've previously seen in fatty acid degradation, adding the CO2 via the enol form. Incidentally, it says that it's a biotin enzyme, so that may have been why we have a carbonyl form of the phosphate. It could also be like in a carboxykinase reaction. Now, here's a reaction that you don't really know or remember. We've made this branched chain 4-carbon thing, and we somehow get a linear 4-carbon thing, succinyl-CoA, out of it. First, we epimerize from D to L. That is lost in the sands of time. I don't know why that epimerization is necessary. But then somehow we move, literally move, a branch to a different carbon. This is a cool reaction. It's a radical reaction. It's one of the first radical reactions you've seen, at least in my class. And it goes via vitamin B12, this gigantic battleship of a cofactor, methylcobalamin. And what methylcobalamin's sole job in the world, all 2,000 Daltons of it, is to create radicals which can be transferred to carbons. In this case, it forms this tricyclic intermediate that essentially allows you to swap one carbon for another. So this is the radical chemistry of taking methyl-malonyl-CoA to succinyl-CoA via this tricyclic intermediate. This is not too hard for you to understand. A, because you have it in Barrick's class, and B, because it really isn't that difficult. So I would advise you to look closely at this radical-based reaction to see if you truly understand it, because it may show up in other junctures. Methylmalonyl-CoA becomes succinyl-CoA, succinyl to semialdehyde. Oh, how boring, we've seen that. So hydroxybutyrate, we've seen that. Hydroxybutyryl-CoA, we recharged it with CoA via our trick of adding a phosphate and bringing in CoA. Crotonyl-CoA. What's happening in this step? Paul Nguyen. Paul, sorry, you're way in the back. Paul, what's happening here, way down here, when we go from hydroxybutyryl-CoA to crotonyl-CoA? The dehydration. And that is formally similar to what we saw here when we went from 4-hydroxybutyryl-CoA to crotonyl-CoA. So we're seeing some of the same reactions show up. Is that the same happening? Yeah. Oh, no, sorry. 4-hydroxybutyryl-CoA versus crotonyl. Yeah, so same type of reaction. Now, if you look carefully at that, Paul, is the double bond where you'd expect it to be? Dehydrate it in your head and tell me if the double bond is where you'd expect it to be. No. You might think about how it got there. Maybe it's a two-step reaction, dehydration followed by a rearrangement. Readdition to give us 3-hydroxybutyryl-CoA, acetoacetyl-CoA, blah, 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 just like the other pathway. All right, 5 of the 6. And the reaction you picked up along the way was radical-mediated carbon rearrangement by vitamin B12. Vitamin B12 is a totally amazing cofactor. It's one of these exception proves the rule thing. It's a very strange cofactor. It's probably left over from the sand, from the ancient sands of time, because it's just so big and complex, right? One of the things we'll get at later in the term, throughout the term, is where do cofactors come from? Where did this thing come from? It's porphyrin ring. It's like a porphyrin ring structure, but it also has nucleotides in it, dimethylbenzimidazole. On top of here, this is currently charged with cyanide, but on top of here, there's often an adenylyl cofactor. This is obviously a nucleotide, has a riboside on it. This thing is just crazy. So this thing is nature's way of carrying around carbon radicals. Nature has other ways of carrying around carbon radicals. This is just probably a really old one. Cofactors are cofactors, right? They're meant to help with chemistry. But sometimes their history is buried in their structure. This is an awful lot of structure to carry a carbon radical. Tyrosine would do just fine. All right, now, here's the last one that you know about. The 3-hydroxypropionate bicycle. We can ride around our bicycle. Now, in the bicycle here, we're going to see some stuff we've already seen. Acetyl-CoA to malonyl-CoA. Old stuff. To 3-hydroxypropionate. Wait a minute here. Well, first of all, the CoA popped off to make malonate. And 3-hydroxypropionate, oh my gosh, we actually needed 2 NADPHs. We're leaving out a step where we go from malonyl-CoA to malonyl semialdehyde to 3-hydroxypropionate. So there's 2 reductions covered up in there. That's 4, because here we had, we're essentially running through the bicycle 2 things. One half of the bicycle will go this way, one half of the bicycle will go that way. But from acetyl-CoA, we do 2 equivalents to malonyl, 2 equivalents to 3-hydroxypropionate, requiring, since there are 2 reductions, 2 times 2, 4 NADPHs. 3-hydroxypropionate to propionyl-CoA. There we're going to have a dehydration and a reduction. And we're going to re-add the CoA, which popped off somewhere along here. Again, remember I said that CoA just comes and goes. When it goes, it's generally hydrolyzed unless it's kicked off by a hydride. There was no kicking off of a hydride here. This was probably just a hydride. Actually, I guess it could have been a kicking off by a hydride here. It could have been either end of the malonyl semialdehyde. So that's possible. It was kicked off by a hydride there. And then finally, reduction to 3-hydroxy. All right, down to propionyl-CoA, which we've seen before. Going this direction, oh look, it's that radical reaction. It's the reaction where we have, enol form, addition of bicarbonate, could be a biotin-mediated reaction to methylmalonyl-CoA. Isomerization, succinyl-CoA, there's our radical reaction. Succinate, pop goes the CoA. Succinate to fumarate, that's Krebs cycle. Fumarate to malate, that's Krebs cycle. Malate to malonyl-CoA, that's not Krebs cycle. Normally we'd expect an oxaloacetate here. But here we've added back a CoA. And again, really no rhyme or reason. CoA, CoA, not CoA, add CoA back, keep CoA, drop it off, add it back. Sorry, don't know why. Sometimes it's functional reasons. Sometimes the CoA is going to act as a ligand group. In many cases, I cannot tell you exactly why. All right, malleole CoA will now split to acetyl-CoA and glyoxylate. 4 goes to 2 plus 2. Think about that reaction mechanism. I think you'll find that it is very similar to the aldolase reaction mechanism that you already know. Glyoxylate is going to re-enter down here in the other half of the bicycle. So take that glyoxylate and go all the way around here and add it back to propionyl-CoA to make beta-methylmalonyl-CoA. Here, this is also going to be like the reverse of an aldol reaction. It's going to be an aldol synthase reaction to make the beta-methylmalonyl-CoA, which will go to mesophenyl C1-CoA, which will go to mesophenyl C4-CoA. Yeah, that's right. Sorry, it's probably easier to see on the, it's all drawn out. Where's my mesophenyl-CoA? Oh, sorry, it's not this one. It's the other half of the bicycle. There's one half of the bicycle. There's a full bicycle. There we go. Mesophenyl C1-CoA and mesophenyl C4. Really, this is, I don't even know why this happens. We actually go from having CoA at one end to CoA at the other. We add a cross-level bond, hydration, citramallyl-CoA. We split it into pyruvate and acetyl-CoA. So 5 carbons goes to 3 plus 2. Now, this is, so in some ways, counting in the bicycle is very, very difficult. 2 CO2s come in to become glyoxylate. 2 CO2s come in to be glyoxylate. 2 glyoxylates, all right, so 1 plus 1 to 2, 1 plus 1 to 2, 2 glyoxylate, no, sorry, not, this glyoxylate, sorry, it comes at 1 plus 1, 2, there we go, sorry. I need to, This is confusing even for me, keeping count on my carbons here. I'm trying to see if I ever lose a carbon. I don't. So 2 plus 1 goes to 3. 3 goes to 4. That's right. 3 goes to 5. 1. That's right. There we go. Okay. Whew. 2 plus 1 goes to 3. 3 plus 2 goes to 5. 5 goes to 5. 5 goes to 3 plus 2. But in the bicycle, we have first, we make 1 3-carbon compound, and then going this direction, we make that 3-carbon compound into a 4-carbon compound and split it back to 2 plus 2. There we go. It's hard to even say. We did one half of the bicycle, the other half is similarly pretty easy. This, via either a Biotin reaction, goes to methylmalonyl-CoA. We've seen that radical rearrangements, acetyl-CoA, malate, malate-CoA, glyoxylate addition there, methylmalonyl, mesophenyl, citramallyl, and again, an aldol-like cleavage to give pyruvate and acetyl-CoA. And I think you can do the reaction mechanism there. All right, sorry. So the point of that, then test questions. I'm not going to go forward. All right, so let's go back and look at a couple of big picture things here. Right? Here's your summary of reaction types except for radical mediated rearrangement. But when we look at the reactions, again, you know Calvin cycle, you know reductive TCA. This is where we start playing around. But we only play around with a couple of reactions. Right? We add CO2 generally via some enol state to get usually up to a 3-carbon compound. In this case, pyruvate. In this case, malonyl-CoA. In this case, malonyl-CoA. So we get from a 2-carbon to 3-carbon compound, and then we take that 3-carbon compound, malonyl-CoA, and we're going to basically turn it into propionyl-CoA here. We'll go backwards. We're going to turn malonyl-CoA into propionyl-CoA there. And we're going to turn pyruvate into a 4-carbon compound by the addition of another CO2 via a series of reactions, some of which you've seen in gluconeogenesis to get to 4-hydroxybutyrate. Now, this cycle, once we get to propanenyl-CoA, we can go up to 4 carbons as methylmalonyl-CoA, and methylmalonyl-CoA will then itself get to 4-hydroxybutyryl-CoA. That's what's sort of beautiful. You can either go via